In this chapter, we're going to talk about exponential functions and log functions. And these functions, exponential function and log functions, actually are related to one another because they're inverses of one another. So first, let's talk about exponential functions. An exponential function is a function in the form of a to the x, where a is a real number, and actually a must be a positive real number greater than 0 but not equal to 1, because if a equals 1 then you basically just have a constant function. So that's the base has to be a positive number that doesn't equal 1, and then the domain of this function is all real numbers, so x can be any real number. Some examples of this: here you have an exponential function with base 5. Here you have an exponential function with base 1.3, and here you have an exponential function with base 3/4. Now all three of these are exponential functions because notice that the base 5, 1.3, and 3/4 are positive numbers and they don't equal 1. Now other functions in the family would include functions where you have other operations involved, but you do have a base raised to a power that involves a variable. So here 5 to the 2 minus 3t, and then you're multiplying by 100, and so this would be in the exponential function family. Here you have the base is 1 plus 0.05 over 4, and the exponent is 4t, and then of course you're multiplying by 500, and that's in the exponential function family. Now, to graph some basic exponential functions, I want to look at a couple of two basic functions, and there's infinitely many of these we could look at, but let's just look at a couple. First I want to look at is where the base is a number greater than 1, like for instance here the base is 2. So let's look at how we could graph 2 to the x. I'm just going to do a simple table here for x values, -2, -1, 0, 1, and 2. And then I'm going to plug those values in to get the y value. So you can see down here, if I plug -2 in, 2 to the -2 is 1 over 2 to the positive 2, which is 1/4. And then 2 to the -1 is just the reciprocal of 2, which is 1/2. Then 2 to the 0 is 1, 2 to the first is 2, 2 squared is 4. So when x is -2, over here you're going to get 1/4. When x is -1, you're going to get 1/2. When x is 0, you're going to get 1. And when x is 1, you're going to get 2. And of course the 0.24 is off of the graph. It would be up here somewhere. So anyway, you can see that this graph sort of slowly arches upward as you go left to right. And what happens is the farther you go to the right, the quicker or faster the increase is of this function. So, and the other thing you might notice is that as you go left to right, this function is increasing. Now, if you choose a number that's less than 1, now remember it's still got to be greater than 0, but let's say you choose a number between 0 and 1, like 1/4. Well, let's see what happens to the table if I do that. If I let x be -2, 1/4 to the -2 is the same as 4 to the positive 2, which would be 16. And then if x is -1, 1/4 to the -1 is just the reciprocal, which is 4. 1/4 to the 0 would be 1. 1/4 to the first would be 1/4, and 1/4 squared would be 1/16. Well, -2 would be off of the graph because at -2 it would be way up here somewhere. So let's start with -1. At -1 the y value is 4. At 0 the y value is 1. And at 1 the y value is 1/4. And then of course if you go out to 2, you're going to be down here at 1/16. So you can see that this function, as you go left to right, is a decreasing function. Now if I wanted to, I could graph other functions based off of these two base functions, 2 to the x and 1/4 to the x, by using some algebra rules. For instance, if I wanted to graph 2 to the x plus 5, once you replace x plus 5, you would simply take this function, and by replacing x with x plus 5, it would just shift this function over 5 units. So it would shift it to the left 5 units. And then if you wanted to subtract 2 from it, it would shift it down 2 units. So to get this function here, you could get this function based on this function 2 to the x by simply shifting it to the left 5 and down 2 units. Just shift all the points to the left 5 and down 2 units. This function is based on the function 1/4 to the x. When you replace x with negative x, it reflects it around the y-axis, and then when you multiply by -1, it reflects it about the x-axis. So to graph that, you would take this function and you would reflect it around the y-axis. So basically you would have something like this, and then you would reflect it around the x-axis, and so when you did that, you would get something that kind of looked like this. But then after that, you have a plus 5, so by adding 5 to it, you would take the final result and shift it up 5 units. And then this last one here, 5 times 2 to the x, make sure you don't make the mistake of thinking that's 10 to the x, because that's not true. The exponent has to come first, and so you can't multiply the 5 times 2 and get 10. Alright, so basically what this does is the 5 is going to stretch that function by a factor of 5. So if you take the base function 2 to the x, this point, which is 0, 1, would be way up here, which is 0, 5. And so it really would stretch it like that by a factor of 5. And that's how you can graph these functions using the algebra rules for graphing. The properties of these functions are pretty straightforward. The domain of these functions are all real numbers. So if you look at either graph here I've got one graph where the base is between 0 and 1, and here the base is greater than 1. Well, both of these, the domain, you can put in any x value for either one of these functions and get a corresponding y value. So the domain's all real numbers. Now the range is only the positive real numbers. In other words, from 0 to infinity. So you'll notice that the graph never actually touches the x-axis, nor does it cross the x-axis. So the y values cannot be 0 or negative. The y-intercept on both of these is the point 0, 1. So that's always going to be the y-intercept. The x-axis here is basically what we call a horizontal asymptote. And so, in other words, the graph gets infinitely close to the x-axis but never touches it. And f is an increasing function if a is greater than 1. So like you saw with 2 to the x, here if a is greater than 1, it's increasing. And if a is between 0 and 1, it's decreasing as you move left to right. And then the last thing I want to show you is that this is a one-to-one function because it passes the horizontal line test. So a horizontal line never crosses it more than once for either one of these graphs. So these are both one-to-one functions, which means they have an inverse. One particular base that we're interested in mathematics is the base e. And e to 5 decimal places is the number 2.71828. But technically, the exact value of e is e because this decimal never terminates. The value e is actually derived from a limit in calculus, which in an algebra course you generally don't have to worry about that. But that's where the limit e comes from. But I won't focus much on that. But what you can do is, since we know e is approximately 2.72, you can either take the number 2.72, or your calculator should have an e to the x key. And to get a more accurate value, you can just tell the calculator you want to get e to the -2, and it'll give you 0.14. And then e to the -1, which would be 1 over e, would be about 0.37. And then e to the 0 would be 1. And then e to the first would be 2.72 if you round it to 2 decimals. and then e squared rounded to two decimals would be 7.4. So if we wanted to, we could graph that up here on the grid, and we could see what it would look like. And notice that e to the -2 is a very small value, less than you would get here for this other graph. And then e to the -1 was about 0.37, so I guess that would be like maybe right here. And then e to the 0 would still be 1, and then e to the 1 would be about 2.7, which would be up here. So if you graph that, let's see if I can just do it free-handed here. If you graph that, it would look something, sorry about that, but it would look something like that without the little zigzag in there. So it looks very similar to 2 to the x, and of course it should, because 2 to the x is basically just 2 to the x, where e to the x is 2.7 to the x. Now, the last thing I wanted to talk to you about was, of course, you could graph some other functions based on this. If you wanted to graph minus e to the x minus 2, you would just take the graph of e to the x and shift it to the right 2 units and reflect it about the x-axis. That's what the -1 does. And then if you wanted to graph this function, the minus x would reflect it about the y-axis. The 2 would stretch it by a factor of 2, and then the +3 would shift it up 3 units. And then the final thing to talk about, make sure you can evaluate functions, exponential functions, on your calculator. So if I had 2/3 to the x and I had to find what is that function evaluated at square root of 11, then make sure you can raise 2/3 to the square root of 11 on your calculator and get 0.261. If my function was pi to the t, where the base is pi, and I wanted to evaluate it at the number e, then grab your calculator and calculate pi to the e and get 22.459. And then if my function was 10 times e to the 1 minus x, and I wanted to evaluate it at x equal -0.05, well, just plug -0.05 in for x, and so you get 10 times e to the 1 minus -0.05, which is actually e to the 1.05. So that would be 10 times e to the 1.05. Plug that in your calculator and make sure you can get 28.577. And so that completes our discussion of exponential functions. In the next section, I'll talk about the inverse of exponential functions, which is log functions.